So, thank you all for coming. I'm going to present the work we did for the past couple of years about optimizing dynamically typed programs or languages. And I'm going to talk a little bit about characteristics of these languages, just a little bit, so we can better understand the challenges we faced when we wanted to try to compile these kinds of programs, these kinds of languages ahead of time in an untraditional fashion, and how we used all sorts of interesting data flow analysis to accomplish this goal. So, a little bit about our contribution. I'm going to present our methodology of obtaining a sound type inference for the TypeScript language, type inference we did in order to be able to compile this language, these programs ahead of time into binary. I will also tell you about how and why did we need to use a sort of pointer analysis, not really a pointer analysis, but tracking objects in our program and where they go. I'm going to tell you about Ductape, the proof of concept implementation of this methodology, and a little bit about our evaluation. So, a short example of a TypeScript function, a JavaScript function, if we'll be accurate, goes through an array and searches for the maximum element of that array. So, one characteristic of dynamic languages, I will say dynamic languages as an umbrella term for any language that is both dynamically typed and because of its being dynamically typed, it needs some sort of a managed runtime to perform these type checks. So the first characteristics is type checks happening during runtime, right? The runtime environment, the interpreter needs to check for each operation, if it's even legal, when we perform it of the certain values we are performing it on. For example, if we assume that our input is an array, during runtime we need to check if it's really an array, if it has the length accessor, if it has the subscript operator, and so on and so forth. For each value, for each operation we perform, we actually need to make sure during runtime that we perform the correct operation over the correct type. Now, obviously, these type checks during runtime, which happens all the time, they do incur a lot of overhead. So one traditional way to tackle this overhead is using JIT compilers. JIT compilers optimize the code that the interpreter runs during runtime. They're very good at it, to be honest. They mostly rely on type information, on runtime type information, and all sorts of metrics the runtime environment gathers during execution. And it typically works for hot zones, and it works gradually throughout the execution of the program. Yeah, as I said, that's one example from one of our benchmarks that I will go into later, but JIT compilers these days achieve speedups of orders of magnitude. The programs run by JIT compilers are order of magnitude faster than the original programs. When we use these JIT compilers, it's actually we actually incur some more checks we will need to do during runtime. For example, in case the max function we use here, in case the JIT compiler decided to compile it during runtime, assuming these values that the max function gets are numeric values, let's say. Now, each time we call this function, we actually need to check the boundary when we transition from the original code into the compiled code, the binary that the interpreter preserves for this function. We need to check the correctness of the types we pass across this boundary. All of this is very common in dynamic languages, and I'm not sure how many of the people in the room are more used to programming in static languages such as C or C++, but in these kinds of languages, in static languages, statically typed languages, all these type checks are performed before the execution, right? By the compiler, by the whatever tool you use to process a linter, I don't know, to process your source code, and in a fashion that the user doesn't feel. It doesn't know about what tools did you pass your program through before execution. And also, this kind of compilation does allow us to invest how much time we even want to we want to invest in these in this processing of the source program, and it does enable us some further optimization opportunities, which JIT compilers do not usually. It's not an option for JIT compilers usually. So for the previous chart I showed you, we add another. If the blue bar, I haven't mentioned it earlier, is a TypeScript program run by a baseline interpreter without any JIT compilation. The orange bar is the speedup we get with a JIT compiler, and the green lower bar is the same program implemented in a different static language, C++ in this case, and it does not suffer like all the overhead of the JIT compiler and the type check-ins and so on and so forth, and it is able to run much faster than that. So we thought, how about we try to take these ahead-of-time optimizations that a compiler usually performs and take these into the world of dynamic languages, okay? To be more precise, can we get a better performance using an optimizing ahead-of-time compilation for these dynamic languages? Now, if we're completely honest, there are solutions, there are all sorts of tools, all sorts of previous work that try to perform ahead-of-time compilation to dynamic languages, mostly for PHP, a little bit for Lua, if some of you are familiar with these kinds of work. The thing is that they do get some speedups, but they don't get the speedups in the same order of magnitude as JIT compilers. So our implicit hope here is, can we get such a good ahead-of-time compilation for these languages in such a way that it will be a viable alternative for using JIT compilers? So in order to do that, we wanted to use existing tool chains. Okay, we didn't want to implement, a complete backend compiler that performs all sorts of complicated optimizations. We wanted to use existing tool chains. We chose using the LLVM toolchain and the C++ compiler that we're all familiar and we all love. And in order to be able to use these kinds of tool chains in an efficient manner, in a way that we will be able to optimize our program, we did need to we found out that we need to represent values in our program in a compact and efficient manner. If we're able to represent numbers as integers, that's way better than representing them as floating points numbers. If we're managing to represent arrays as homogeneous arrays, instead of arrays that contains, I don't know, some sort of dynamic value that can be anything, that will usually be better. So in order to achieve these efficient representations, we wanted to perform a type inference over the source program. Now, for those of you who were here for the ICFP keynote this morning, you've heard that the TypeScript type system is unsound by design. So we figured out, if we do want to represent our programs in binary, if we do want to preserve the semantics of the source program, we cannot rely on these type inference or type checkings that the TypeScript compiler provides, and we want to guarantee the soundness of the translation into binary. We also wanted to use, fixed point algorithms, as we all know and love in the static analysis community. And in order to do that, we did define our own type lattice to use. It's pretty straightforward. I'm sure it won't shock any of you. It does represent all the types, the primitive types that we can use in TypeScript. For example, we have primitive strings undefined as a type. We did split numbers to number and integers. We did decide here to have a finer grained granularity in order to be, again, to be able to represent things more efficiently in the target program. We do have union types and so on and so on. Also, one key part of the tool is inferring array types and all of that. So we also have this side of the lattice for arrays. Yeah, so all of this type domain and type analysis we decided to perform over an IR we have defined, we called Duct.IR. It is in the structure of a graph program dependence graph, which encapsulates both control flow and data flow. It's very low level-ish, I will say. We wanted to encapsulate, first we wanted to encapsulate all the semantics of the source program, all the building blocks of the semantics, all the atomic operations, reading from an object, calling to a function, any basic operation you wish to represent from your source program. I won't go into too much detail of how the graph works, but in general, we have two types of nodes in the graph. Either data nodes, which represents values, or output of operations. For example, literals or operators like binary operators and so on. We also have nodes in the graph that represent basically the control flow of the program, or stages along the execution of the program, such as a startup function, a return from a function. We also have a compound node, such as not sure my laser pointer works, never mind. Compound vertices are those that both result in some sort of a data associated with them, such as an allocation of an array, or an object is associated with the object that is allocated. And it also control sensitive, right? It does matter when do you perform all sorts of object operations and allocations. For the edges, we do have data dependency edges, which data flows into which operation or which function and so on. And we do have the control edges, which describe the control flow along the program. I will ignore, from now on, mostly ignore the control flow, because the data flow is more relevant to the type inference we do. So forgive me for that. So now that we have this IR, it represents the semantics of the source program completely. We have functions, calls, and so on, which I won't show you. Here's another program, example program. We allocate a two-dimensional array, we read from that array, and we store a new value into that array. Then we have the corresponding Duct.IR representation of it. So I would like to show you, I would like to show you how do we do type inference over this IR, which is like the most interesting thing in this work, in my opinion. So first, we're using a fixed point algorithm, right? I will show you in a specific order, the inference in a specific order for this talk, because it's easier for me to explain that way, but obviously the order shouldn't matter, and we run these inference rules until we reach a fixed point. So first, let's say for literals, it's quite easy. We just infer by the type of the literal in the source program, either integers, strings, undefined, and so on. In case we allocate an array, it's quite straightforward that we have an array that contains all possible types that we passed in the construction of the array. Once again, when you have a two-dimensional array, this time it contains arrays of integers, so it will also be an array of arrays of integers. When we load a value from an array, quite straightforward as well. The loaded value may be of any type that the array can hold. So in this case, the load operation will result in an array of integers. When we do store to an array, and here we start with the interesting part. One thing I did mention is that in these kinds of languages, in dynamical languages, for the most part, types can change along the execution of the program. For example, this array that we have loaded from the two-dimensional array, if we loaded an array of integers and we do insert a string into it, now we get an array that might contain either integers, strings, or both, right? So it essentially changed its type along its execution. And now we might think we are already done with the type inference, right? But we kind of missed something along the way. In this program, for example, we switched the one at the start of the inner array into a string, and our inference did not encapsulate the change of types completely. Okay, so we found out that in order to make sure the analysis is sound, we do need to incorporate some kind of a pointer analysis. We call it pointer analysis because that's a common name for it, in literature, and it comes from other languages where you have addresses to represent objects and so on. Here we don't have this notion of memory addresses, right, in TypeScript, but we did find out that we need to keep track of which objects hold what other objects and which values are aliases for different objects and different values in our program. For example, if we load something from a two-dimensional array, then we have an alias for one of the items this array holds, right? So in our case, we know that if we allocate an array, now every value we pass to the construction of the array is a member of this array, a member of this object, okay? Also, if we load something from an array, we know that now the load vertex, the load node, may refer to any of the loaded objects of the objects the array holds, right? And so on and so forth. Yeah, once again, when we store something to an object, now this object can hold the string in that case. And the interesting thing here is how this affects our type inference. For example, if we found out that the allocation node now might hold the string as a member, then now we can propagate the change of types across the graph. So now our allocation represents an array of either integers or strings, and the outer array also, we can propagate this type information through the graph. And now we're done. Now the duck here is happy. So the proof of concept implementation for this methodology, we call it Ductape, which is sorry? Oh, okay. We call it Ductape, which basically says that we really want the acronym to be something nice. It has three main parts. The front end that basically construct the graph, the duct.ir out of the AST that we get from the TypeScript compiler. We also have the static analysis module that implements the type inference in the pointer analysis that I've described so far. It is implemented using Souffle data log engine. For those of you who are familiar with it, we basically represent the graph as relational database, relations, just tables of the data we collect. And then we can describe the analysis using very simple rules. It has all sorts of nice features, such as built-in fixed point algorithm, lattice support, all sorts of nice features. And the backend is pretty straightforward. We translate this graph along with the type information into binary. I won't go too much into that. So for our empirical evaluation, we measured execution times of all sorts of some TypeScript programs in 4 execution. Actually, I will just jump a little bit forward. We use the ostrich benchmarks. What we really liked about this benchmark suite is that it had both implementations in TypeScript, or JavaScript for that matter, and also handwritten alternative implementations in C or C++. So we could also compare our results into handcrafted native implementations. Out of which we took 6 benchmarks we managed to support with our tool. The other 6 benchmarks were either using features we couldn't yet support, or that the analysis didn't manage to completely infer all the types for these benchmarks. So here in this graph, we see the leftmost bar is the baseline interpreted non-jitted execution. After that, the orange one is execution with a JIT compiler. The third one from the left, the green one, is our results, the results we got after compiling the source program with Ductape and then executing the binary that we got, and last, the handcrafted native implementation. So we found out that in some cases, we got a substantial speedups using our methodology. In some of which it's even, like the previous one, in some of which it's actually getting very close to the performance of a JIT compiler. The thing is, we didn't get these results for all benchmarks. For example, in one benchmark, we even got a slowdown, which we didn't expect. We did dig into the reasons. I won't go too much because I see that I'm out of time already. But we do see that there is a lot of place to improvement as well here. So to conclude, we did, on average, get a ×5 speedup, comparing to the unjitted version. And in some cases, we got results that are comparable to the JIT compiler. I think that's it for today. Thank you very much. Sorry for taking of your time. And that's it. Any questions?
We don't have much time, so one quick question.
Hello, so thank you for the talk. Can you comment a bit more on the benchmarks? And do you have any idea why you have the speed up in some cases and why you don't have it? Like, do they have a specific shape, or they are more dynamic and more polymorphic?
Yeah, so one reason we found out that we had actually a slowdown in this benchmark, for example, is the way we represent objects. We put a lot of effort into representing arrays in an efficient manner. In our case, and we did also add supports for general objects, but in this case, in this benchmark that implements a BFS search for just general JavaScript objects, these aren't represented as classes or anything like that. We did just in order to support these language features, these general objects. We implemented them in our backend as just regular maps from strings to whatever value the map holds. And obviously, this is not the most efficient way you can represent objects, especially objects that usually keep the same structure. So there is some additional work to do here in order to make these cases more efficient. The cases we did manage to have a very good speedups is workloads that use mostly arrays and array operations and stuff like that we do quite good.
Okay, so let's thank the speaker.